This video presents a parameter estimation exercise. It consists of two parts. In part 1, the background of the parameter estimation theory is introduced. Most engineering models have parameters, like those describing environmental processes. The generic description of the model of a physical system is shown in the figure. It has a boundary with inputs u and outputs y, and a mathematical model that describes the transformations coupled with mass balances. As such, parameter estimation is an inverse problem that can be defined as: given a set of output measurements y, estimate some unknown parameters θ of model f. There are several statistical methods to estimate parameters. One of the most commonly used methods is the frequentist approach. In this method, the parameters θ are treated as true with fixed values. But their estimators θ hat are considered random variables. Because the measurement errors can be considered stochastic, for example, the outcome is based on a chance process, then the measurement errors can be defined by distribution functions, like a normal distribution with mean, zero and variance, sigma square. The maximum likelihood estimation is a mathematical formulation for parameter estimation within the frequentist framework. Maximum likelihood estimation assumes that the measurement errors are normally distributed, and it selects a multivariate normal distribution as the likelihood function. At the left-hand side, the likelihood value can be found. In this case, the likelihood value represents the probability that a given θ estimate can describe the dataset y. The higher the likelihood value, the higher the probability that the proposed θ values describe the data y. In turn, this means the higher the likelihood that θ hat approximates the true values of the unknown model parameters θ. Numerically, θ hat is found by a search algorithm that maximizes the likelihood function. The least squares is a special case of the maximum likelihood estimation method. In the least squares method, the measurement errors are assumed to have white Gaussian noise, in other words, that the mean is zero, and that they are identically, independently distributed. In this case, the likelihood function is simply equivalent to minimizing the sum of the square errors or loss function. The solution to this minimization problem will identify the values of the parameter estimators theta hat. A parameter estimation problem does not end when the solution for the minimization problem is found. It is just beginning. One needs to analyse the statistical quality of the parameter estimators themselves considered random. The estimation of the covariance matrix of parameter estimators, cov theta hat, is the cornerstone for this purpose. The covariance matrix can be estimated by first-order Taylor series approximation of the model F around the minimum point. The partial derivative of F with regard to theta provides F, which is the Jacobian matrix of the system. The multiplication of F transposed with F is also known as the Fisher information matrix, FIM. The covariance matrix combines information from the residuals, sample variance of the residuals, and sensitivity of the parameters to the model around the minimum point. In any case, the residuals and the minimum cost function value are mapped as errors to parameter estimators according to their sensitivity functions. To summarize the parameter estimation theory, it can be concluded that parameter estimators are considered random variables because of the stochastic nature of the measurement errors. The difference, and therefore the parameter estimation error, between true parameter values and their estimators follows an asymptotically normal distribution with mean zero and a certain covariance matrix for a large sample of n. The covariance matrix, cov theta hat, is estimated by first-order linearization of the system around the minimum point. This relies on the assumptions that errors are identically independently distributed, with mean zero and certain variance sigma square. The estimated sample variance sigma square itself is a random variable that follows a chi-square distribution with n-1 degrees of freedom, because squared normal variables follow a chi-square distribution. Finally, the confidence intervals for parameter values can be estimated at a given alpha significance level by referring to a student t distribution. In this lecture, the basic formulation of the parameter estimation theory within the Frequentist school has been reviewed. Building on this basis, there are different approaches to the maximum likelihood estimation formulation. The generalised least squares, GLE for example, updates the covariance matrix of measurement errors at every iteration of the parameter estimation problem. GLE usually takes longer to converge, but if measurement errors are assumed to be known, this is the recommended method. Robust regression deals with the effect of outliers in measurements and weighs them in such a way that they do not influence the outcome. Ridge regression helps with ill-conditioned optimization problems, which is an important numerical issue. In this video, the theory of parameter estimation is applied to an ammonium oxidation batch test. Here, the framework used to bring the theory to practice is presented. The workflow contains 5 steps, iterative in principle since PE is an open problem. In step 1, initialization, a model to describe the system of interest is selected. These models are often coupled to algebraic and ordinary differential equations, ODE, or sometimes to partial differential equations. Also in this step, the initial conditions of the state variables and nominal values for parameters are defined. In step 2, data for estimation are selected and reviewed. Preferably, data should be quality checked before being accepted for a PE routine. The parameter subset is also selected either by expert judgment or sensitivity or identifiability analysis. In step 3, a cost or objective function is formulated and solved using numerical solvers. In step 4, the covariance matrix is calculated and used to compute confidence intervals and the correlation matrix for the estimators. In step 5, the model fits are plotted using the optimal parameter values and they are compared with the data. It is also reviewed if the parameter values are within typical ranges reported in literature. If the results are not satisfactory, for example, if they are abnormal values not having any physical meaning, or if the model fits poorly to data trends, then the workflow needs to be iterated by going back to steps 1 or 2. Remember that this is an open problem, so we need to iterate until the data converge. This is the model selected to describe the ammonium oxidation process in a batch test. The ASM framework is used to model a system. The model considers a 2-step nitrification process with growth and decay rates, in addition to a gas-liquid transfer rate for oxygen transfer. Since this is a batch process, input and output mass flows are 0. Hence, the mass balance equation is simplified to simple conversion terms. 6 ODE equations represent the system dynamics as a function of time. These are implemented in MATLAB as a script function. Thereafter, the initial conditions of the model are described. They correspond to the initial operating data of the batch test itself. Information about the conduction of the batch tests should be obtained from the people in charge of the execution of the tests. There is an addition of ammonium in a pulse mode of 20 mg of nitrogen per litre. Oxygen is saturated and therefore reaches 8 mg per litre. Nitrite and nitrate are initially not detected and thus assumed to be zero. Biomass concentrations are predicted to be 75 and 25 mg of COD per litre respectively for AOO and NOO. These initial conditions are saved in a file named init.const.m. In the next step, the nominal values for the parameters of the model are gathered. We also provide the lower and upper bounds. These values are obtained from a literature survey. The range for KLA, however, comes from batch tests and the aeration system itself. These data are saved in the file init.const.m. The experimental dataset for the parameter estimation needs to be reviewed. We use data collected from batch test 1, which includes ammonium, nitrite, and dissolved oxygen measurements. Due to the suppression of NOO activity, no nitrate production is observed. Since batch test 1 is not designed for the estimation of the decay rate coefficient, we consider all the parameters of AOO, except BAOO for parameter estimation. For instance, the following parameters are selected. Y has ammonium, nitrite, and dissolved oxygen measurements, and theta has the parameter subset of data that contain YAOO, mumax AOO, KSAOO, and KOAOO. This data is retrieved and plotted in a MATLAB script file named example5_3 part1.m. For step 3, the objective cost function is formulated as a sum of the squared errors between measurements and model predictions. Since we have assumed that the measurement errors follow a Gaussian normal curve with known variance that is constant and does not change during the test, this simplification will not alter the solution. This objective function is formulated in the costf.m MATLAB script function. If this optimization problem is solved using the fmin search algorithm in MATLAB, this part is implemented in the file example5_3 part1.m. The outcome of the solution is the optimal values for the parameter estimators shown in the table. The quality of the parameter estimation approach for the ammonium oxidation process is presented in this table, together with the standard deviation, 95% confidence intervals, and the correlation matrix. This information was obtained from the covariance matrix for parameter estimators. These computations are implemented in the file example5_3 part1.m. Thus, the results are plotted from the model fits to the data, where the model fits are obtained using optimal parameter values. In practice, there are several typical pitfalls. These are the following. First, the measurement errors often autocorrelate. This means that too many observations are redundant and not independent, non-IID. One solution can be to check the autocorrelation of the residuals and filter subsample to reduce the autocorrelation in the measurement dataset down to, for example, 0.5 and lower. Second, the parameter estimation algorithms may stop at local minimum values. To find a solution, use several search algorithms, a multi-start strategy, and global search algorithms to ensure that the minimum of the cost function is reached. Finally, there are identifiability ill-condition issues, so that not all of these parameters can be estimated uniquely. As a solution, an identifiability analysis or parameter transformations need to be performed to simplify the model. The best practice is always to verify the parameter estimation results with another independent estimation method, like the bootstrap method presented in the next video lecture. Further reading on the topic is recommended. Interested readers are referred to this list of references, which is by no means a comprehensive one. In the current folder, we can see 6 files implementing parameter estimation in MATLAB. The main file is example5_3 part1.m, which executes all the workflow, including the subfiles. The costf.m includes the cost function for the fmin search algorithm. The coftl.m includes the cost function for the lsqnonlin algorithm. This is used to verify the solution of fmin search and to provide the Jacobian matrix, which is used to compute the covariance matrix. Data AOO.mat includes the experimental dataset. initdcond.m contains the initial conditions and nominal and upper and lower ranges for parameters. nitmod.m is the file that contains the nitrification model. All these files are available as part of the online course. As shown before, the 5-step workflow will be executed in the main file. First, the highlight mode is selected to execute step by step. Click Run and then click Step. This function will clean the workspace and figures if there are any. Next, the experimental data is loaded and reviewed by plotting. The experimental data contain the measurements for ammonium, nitrite, nitrate and dissolved oxygen. Now the results are plotted and saved as figure 5.2. Thereafter, step 1 of the workflow is executed by loading the initial conditions file initdcond.m. This will load to the workspace the nominal values, parameters range, and initial conditions. In step 2, the data to be used for estimation is selected. The indexes 1, 2 and 4 are specified, which refer to ammonium, nitrite and dissolved oxygen, respectively. The data matrix can be selected by positioning the cursor over the YD matrix. Next, the parameter indexes for estimation are selected. One, 2, 3 and 4 are selected for the yield, maximum growth, substrate and dissolved oxygen affinity, respectively. Then the lower and upper ranges for these parameters are retrieved. The initial guess to start the parameter estimation is selected or defined, pin it, in between the lower and upper ranges. In this exercise, the initial guess starts at 1/3 in between the lower and upper ranges. The fmin search solver is run. The termination criteria for optimization is specified by the command options. For example, a typical termination criteria for the cost function is shown that corresponds to 1 times 10 to the power of -6. Next, the fmin search solves the cost function by starting at the initial guess and using the selected data, td, yd, iy, and parameters idx. When the fmin search is executed, the progression of the search algorithms is displayed. The final cost function values, as highlighted in the last row, can be seen. Moving the cursor onto pmin, the optimized values can be seen. On SSE, the sum of the square error can be seen. LSQNONLIN is executed to verify the solution. Now, the search algorithm will start with the optimal solution previously found. In this screen, it can be seen that the optimal solution did not change, confirming that the optimal solution had been found. Thus, the final results of the parameter estimation are displayed on the command window. They can be compared with the initial starting values. In the next step, the covariance of the parameter estimators are computed. For this, LOSQNONLIN.m is used with no iteration that computes the Jacobian pmin, the optimal solution. The degrees of freedom and variance of errors are computed, and they are used to compute the covariance matrix PCOV. The diagonal of the PCOV matrix is the variance of the parameter estimators. The correlation matrix of the parameters is also calculated. The 95% confidence interval is estimated. The t-distribution value at 0.025 probability level is calculated and used to compute the p95. The results are displayed in the command window. This is the correlation matrix. The results are plotted. The linear error propagation maps the parameter errors, pcov, to model prediction errors, ycov. Similarly, the standard deviation of the model, y sigma, and 95% confidence interval of the model outputs are computed. Then the results can be plotted and saved. This concludes the parameter estimation problem. It is recommended to check the quality of the results as suggested in the textbook. Do not forget to save your results.